In this second part of countable sets and uncountable sets, we will prove that the set n cross n, the Cartesian product of n with itself, is a countably infinite set. Then we will show that the set of positive rational numbers is countable. Then we will prove that their countable union of countable sets is countable, and using that we will show that the set of all rational numbers is countable. Further, what we will do is we will show that the open interval 0 1 is uncountable, and conclude from there that any interval in the set of real numbers is uncountable, and in particular the set of real numbers is uncountable. So let us start. First of all, you notice that if I look at the Cartesian product of n with itself, then I can arrange the elements of n cross n in an array of this form, where the first row consists of those elements of n cross n whose first coordinate is 1. The second row is where the first coordinate is 2. Third, third row is where the first coordinate is 3, and so on. So we have arranged our n cross n in this lattice or array form, and then you see that I have somehow color coded this whole array in certain fashion. So what I am doing is that I am going to look at diagonals of this form in this array. So the first diagonal will consist of only one element, 1 1, and this I call D1. So D1 is the set which consists of those elements, so that when you add the first coordinate and the second coordinate, then you should get 2. So the only possibility is just 1 1. Similarly, the second diagonal would consist of those elements where you when you add the first coordinate and second coordinate, you should get 3. So notice that in general, Dn would be the set of all those elements of n cross n, where the sum of the first coordinate and the second coordinate is n plus 1. So I have 1n, 2n minus 1, 3n minus 2, and so on till n1. So D3 is going to be this one, where the sum is 4. This is D4, where the sum is 5, and D6, so it will continue from here and it will continue till some element here. So in this fashion you will get all the diagonals. What we are going to do is we are going to describe a bijective mapping from n cross n to the set of positive integers. And how are we going to do that? If you just look at this picture again, this will just send 1 1 to 1, this to 2, this to 3, then 4, 5, and 6. So this is the way we are going to count. So 1, 2, 3, 4, 5, 6, and 7, 8, 9, and 10, and so on. So this we will make precise. So let us see how to do that. So you have seen that we have described certain subsets, finite subsets consisting of n elements of n cross n, which are those for which the first coordinate and second coordinate, if you add, you get n plus 1. Very good. So using this, what you do is you'll use some certain formula like this, but the basic idea I have already told you. So define a mapping f from n cross n to n as follows. Just look at any I comma j, you send it to this formula. Okay, so just notice that if I fix this to the elements of Dn, then I plus j is n plus 1. That is what we have observed. So where will any element ij of Dn go? It will go to n plus 1 minus 1. So n into n minus 1, right? So I plus j is n plus 1. So n plus 1 minus 2 is going to be n minus 1. So this will go to n into n minus 1 by 2. And to make it injective, we add this indexing, so called plus I. So if you look at uh, where dn is going to map, it is just going to n into n minus 1 by 2 plus 1, n into n minus 1 by 2 plus 2, and so on, till the last one will be n into n minus 1 by 2 plus n. Because if you are looking at elements of dn, I ranges from 1 to n. See, that is what we had uh, done here. That if you look at dn, its first coordinate is going to start from 1 and go on till n. So you are going to send the elements of dn via this map f to exactly this particular set. So let us see what is this set. If you put n is equal to 1 here, then so I have called this set an. So a1 is going to be when n is equal to 1. So if n is equal to 1, this n into n minus 1 by 2 becomes 0. So the only thing which is left out is this 1, and it will start from 1 and end at 1. So a1 is just going to be 1. What is a2? A2 is 2 into 1 by 2, so that you get a 1 here. So you will get 1 plus 1, and you have to end at n. So n is 2 here. So you start with 1 plus 1, and the next element will be 1 plus 2. So you will just get 2 and 3. Similarly, what will be A3? A3 will be when you put n equal to 3 here, so it becomes 3 into 2 divided by 2. So this part is just 3. So you start from 3 plus 1, and you get 3 plus 1, 3 plus 2, and 3 plus 3. So that is 4, 5, 6. Similarly, you can just check that A4 is going to be 7, 8, 9, 10. So what I said, that is what we have made precise here, that 1 1 is mapped to 1, this is mapped to 2, and this to 3, then 4, 5 and 6 are the images here, then 7, 8, 9, 10 are the images here, and so on. So all you have to now check is that this mapping f is a bijective mapping. So that is some straightforward calculations. So let us do that. What I have done is that I first of all notice what is quite obvious here, that all these AIs are going to be pairwise disjoint. So what have I said? I have said that if I take any k between 1 and n minus 1, then if I look at n minus k into n minus k plus 1 divided by 2, then this is going to be strictly less than n into n minus 1 by 2 plus 1. This is quite straightforward, because the maximum value it will have in is when k is n minus 1, and when k is n minus 1, then this is n, right? N minus 1, sorry, it is 1, and here it will be n minus 1. So it is how much? Uh, 1 plus 1, so this is 2. So when you put n minus 1, it won't be the maximum, I am sorry, because we have a negative sign here. It will be the minimum value which it will take, and when you put any k is equal to 1, then you will get the maximum value, that is n minus 1 into n minus 1 plus 1. I hope I am clear here. Since I am subtracting a k and a k minus 1, so the maximum value will be when k has the smallest value, that is at 1, and so it is n into n minus 1 by 2. That is the maximum value it will take, so it is going to be strictly less than n into n minus 1 by 2 plus 1. So if you look at a n minus k, a n minus k is going to end at n minus k into n minus k plus 1 by 2, right? So it is going to end at this particular number, and your an is going to start with n into n minus 1 by 2 plus 1. So very precisely you have shown that if you take any k between 1 and n minus 1, then the intersection of an minus k and an is bound to be empty. So an minus k and an are going to be disjoint for any k between 1 to n minus 1. So it justifies that each of these iaj's, they are all going to be pairwise disjoint. Now dn is mapping onto an, right? That is what we have got. That dn had n elements, and here also you have n elements, notice. And the first the way we arrange the elements, we cannot talk about the first element or the second element of a set, but since we have finite set, we have arranged it in a certain fashion. So this 1n is going to map to n into n minus 1 by 2 plus 1. 2n minus 1 is going to map to this one, and so on. So finally n1 is going to map to this one. So in this way, the dn to an, if you just restrict your map f, which is on the whole of n cross n, to this subset of n cross n, then it is mapping dn injectively onto an. So there is a 1-1 correspondence between dn and an, right? And not only that, if you look at n cross n, this is going to be the union of all the diagonals dn. It is quite clear. And the set of positive integers is the union of all ans, because dn's consisted of all I comma j, where I plus j is equal to n plus 1, and any element of n cross n would look like that. So this is clear. And similarly, if you look at the way you have got your ais, you have just partitioned your uh, positive integers in this fashion. So the first one consisted of only one element, the second one consisted of 2 and 3, then you had 4, 5, 6, then you had 7, 8, 9, 10. The next one would be what? It would consist of 5 elements. It would start with 11, so 11, 12, 13, 14 and 15, and so on. So you have just partitioned your set of positive integers in these a1, a2, etc. So n is equal to union of ans, and n cross n is the union of dn's, and from dn to an you are getting a 1-1 correspondence. So therefore f is actually a bijective map. This proves that n cross n is countable. This is a very nice visual proof actually. If you forget about this part of the detailed arithmetic or set theory which we have done here, uh, it is easy to visualize this. Apart from this, you can give another proof also of the fact that n cross n is countable. In fact, there are several proofs. What you do is just take any n comma m and send it to 2 to the power n, 3 to the power m. So what will, why 2 and 3? Because 2 and 3 are two prime numbers which are different. So they are two numbers which are co-prime to each other. So what you will be able to show very easily actually, that if you look at n comma m going to 2 to the power n, 3 to the power m, then that mapping will also be a bijective mapping. So that is another way to show that n cross n is a countably infinite set. And this is one proof which we have discussed in detail here. So I have written n cross n is countable, but you understand that it is actually countably infinite. It is an infinite set which is countable, and by countable set we had meant any finite set or any countably infinite set. So this particular statement is perfectly all right. Okay, so let us proceed. The next result is that once you have that n cross n is countable or countably infinite if you like, then you can immediately show that the set of positive rational numbers is also a countably infinite set. So recall our notation which I had used in some previous lecture, that I took the set of rational numbers and put a greater than 0 as a superscript to mean the set of all rational numbers which are positive. So this will be our notation, and what we will do is we will define a surjective mapping from n cross n to the set of positive rational numbers, and that is very straightforward thing to give. Just take any n comma m and send it to m by n. So clearly this is surjective. Notice it is not injective, because any positive rational number has several forms. Say, for example, if you look at 2 by 3, then 2 by 3 can also be written as 4 by 6. So 2 comma 3 will map via h to 2 by 3, and also 4 comma 6 will also map to 2 by 3. So this mapping is not injective, but it is surjective. Given any positive rational number, it is going to look like some p by q, where p and q are positive integers. So there is at least one p comma q which will map to p by q. So it is surjective. Again, since n cross n is a countably infinite set, recall in our previous lecture we had given the characterization that that means that we will be able to get a surjective mapping from the set of positive integers to the set n cross n. This will be, there is an what we are saying is that there is an existence of such a surjective mapping. What this surjective mapping looks like is not pertinent here. So all you are saying is that there is a surjective mapping from the set of positive integers to n cross n, since n cross n is countably infinite. So now you just look at the composition. You have G surjective from n to n cross n, and H you have actually specifically defined from n cross n to the set of positive rationals, which is surjective. So the composition from the set of positive integers to the set of positive rationals is also surjective. Composition of surjective mappings is a surjective mapping. So again, using the characterization which we had discussed in the last lecture, this implies that the set of positive integers is countable. Very nice. So now, as I claimed, we will be actually showing that the set of all rational numbers is countable. So there is a 1-1 correspondence between the set of positive integers and the set of rational numbers. This is a surprising result, because naively, if you think of it, there is a unit distance between the natural numbers. In some sense, you have 1, and then after a unit distance you just plot 2 and so on, whereas rational numbers have the property that between any two rational numbers there are infinitely many rational numbers. Even then, you can show that there is a 1-1 correspondence between the set of rational numbers and the set of positive integers. So things do become quite counterintuitive when you are looking at infinite or infinity in mathematics. So this is one example of that. So before doing that, we have to prove one result, which says, if you just say it tersely, not very precisely, that countable union of countable sets is countable. So what does that mean? That means the following, that you start with a collection of countable sets. Now that collection itself should be countable, meaning that you have and a set which is countable, say capital I, this is called the index set, and corresponding to every little I belonging to I, suppose capital AI is a countable set. It may be finite or countably infinite. Okay, so that is the meaning of a countable collection of countable sets. That is, each set which you are considering is a countable set, and how many such sets you are considering? You are considering countably many such sets. So you look at this, and what we want to say is that the union of all these AIs will be a countable set. That is our result, and that said in a simple form is like is that countable union of countable sets is countable. Okay, so how will you do that? First of all, notice that AI is a countable set, so there is a surjective mapping Fi from the set of positive integers to AI for every I. Again, capital I is a countable set. There are countably many of these, and that is determined by the index set capital I. The indexing is given by these subscripts. So there is another surjective. You will be able to get a surjective mapping from the set of positive integers to I also. So now use these Fi's and G to define a mapping from n cross n to the union of all the AIs. How do you do that? The mapping is denoted by phi here, and when I write it like this, it means that the element mn maps to something. So instead of writing phi of mn equal to that, we use this notation sometimes to describe a mapping. So that is what I have done here. So what is phi of mn? You look at fgn. So g of n is going to be an element of I. So corresponding to that gn, you look at fgn. Fgn will be a mapping from the set of positive integers to agn, the gnth set in some sense. So fgn of m will be the element where it will map. So I hope I have been able to tell you what I'm trying to say. Suppose uh, I had, instead of I, if I had n, say for example, then I would have a1, a2, etc., something like that. So if I look at 1 comma n, then g, it would map where first you look at where is g of 1 going. So g of 1 will be some index, and corresponding to that index you look at the mapping f of g1. So that will map n to a 1, no sorry, ag1, right? So f of g1 is a mapping from the set of positive integers to ag1. So you look at where m is going under that mapping, that will be the image of mn under phi. This is our description. Okay, so I said that if you take I to be a set of positive integers, it is easy to visualize, but it is not really necessary for any countable set. This is okay. And why I am saying that for any countable set? Because I also could be a finite set or a countably infinite set. So it is not necessary that I is infinite. It could very well be a finite set. It could also be empty, but in that case, this is empty. There is no such collection. So the whole result collapses. It becomes a trivial thing. So we don't bother about that. I have not specifically mentioned that, but it is obvious from our description that if I is empty, then obviously there is no collection in hand. So there is no question of taking the union of that. That would be empty. And so it your union so called is an empty union, so it will be countable. Anyways, so let us talk about the non-trivial part, that you have got such a mapping. Now I want to claim that this is a surjective mapping. How do you see that? You have to take an element from here and show that there will be something which will map to this. So suppose I take some little a in the union of AIs, then that little a is in the union, meaning that there will be at least one I. See, there is no question of these AIs being disjoint or anything. So it could be in several of them. So at least there is one little I such that little a will belong to capital AI. So corresponding to this I, you will be able to get an little n here so that Gn is equal to I, right? So look at that look at that n, and then look at f of Gn, so that becomes f of I. So let us go over it again more slowly. That suppose I take any element here, little a, then it will belong to at least one ai. So you look at that particular index I, then that belongs to capital I. So there will be a little n here such that Gn is equal to little I, because G is surjective. So now you look at f of Gn, this mapping, so that is just fi. So your little a is sitting inside ai and fi is surjective, so you will be able to get a element little m in the set of positive integers, so that fi of m is equal to a. So therefore you have got a little n from here, so that Gn is equal to I, and then you have got a little m here such that fi of m is equal to a. So what have you got? That m comma n is mapping to f gnm, which is equal to fi of m, which is equal to a. So take any element from here, you are able to get at least one element in n cross n, m comma n, so that phi of m comma n would be equal to little a. So pre-image of any element of union ai is non-empty, so that means that phi is a surjection. So you have got a surjection from n cross n to union ai, and n cross n is countably infinite. So there is a surjection from the set of positive integers to n cross n. So again you take the composition. So from n to n cross n you have a surjection, and compose that with this map phi. So you get a surjection from the set of positive integers to the union ai. Therefore, by that characterization, what have you got? That union of ai is countable. So if you take a countable collection of countable sets and take its union, then you will again get a countable set. This is your result. So how are we going to use this result for the set of rational numbers is quite uh, uh, straightforward now. What you do is, using similar type of notation, let q less than 0, like this, less than 0 in the superscript, be the set of all rational numbers which are negative. Then you can get a 1-1 correspondence between the set of positive rational numbers and the set of negative rational numbers, just by sending every q to minus q. So call this map f. So in our language, we can say that the set of positive rationals and the set of negative rationals are equipotent. So we can get a bijective map from here to here. So if you we have already seen this. I have again written down in details that since these are equipotent, so, and we have already seen that the set of positive rationals is countably infinite, so it follows that the set of negative rational numbers is also countably infinite. So I have written it in detail that since this is countably infinite, so there will be a bijective mapping from the set of positive integers to this. Just take the composition. First you look at G, which maps n to q greater than 0, and compose it with f. You will get a mapping from the set of positive integers to the set of negative rational numbers, and this will be bijective. So therefore the set of negative rational numbers is also a countably infinite set. So what have you got? You have one countably infinite set, which is the set of positive rationals. You have another countably infinite set, which is the set of negative rationals. And then you also have a finite set, which consists of only the element 0. So if you take the union of all three of these, then you will get the set of rational numbers. So you have three countably infinite sets, and you are taking the union of that. So since there are only three, you have a countable union of countable sets. So therefore Q is countable. That is the result. So you have proved that the set of rational numbers is countable. Now we will give you the first example of an uncountable sets. This result has several proofs in literature. The one which we have chosen here is the Cantor's diagonal argument. This is very beautiful. So let us see how we do this. We are going to use the fact that any real number has a decimal expansion. So my interval is open interval 0, 1. So that means the real numbers are greater than 0 and less than 1. The set of all real numbers between 0 and 1. That is my set. And I want to say that this is an uncountable set. So the way we are going to prove this is by saying that there cannot be a surjective mapping from the set of positive integers to this. So we know that there is this uh, characterization that see, first of all, this is an infinite set. That we know, because between any two real numbers there are infinitely many real numbers. So therefore this is an infinite set, and we want to say that it is not countably infinite. So we will just say that there is no surjective mapping. That is the characterization from the set of positive integers to the open interval 0, 1. So how will you show that? You assume that there is, you just take arbitrary mapping from the set of positive integers to 0, 1. So if you take this, for every n, Gn is going to be some real number between 0 and 1. So just give it a name. So suppose G1 is mapping to 0.x11, x12, x13, etc. G2 is mapping to 0.x21, x22, x23, etc. and so on. So you can just name what your image of 1, 2, 3, etc. are going to be. So do that. Now what you do is you construct a decimal number. How? You just suppose y is equal to 0.y1, y2, y3, etc. Where yi's are what? Let yn be equal to 1 if x and n is not equal to 1, and let it be equal to 2 if x and n is equal to 1. So that means what? You just look at y1 first of all, then you look at what is happening to G1. So G1 has this x11 here. So if x11 is equal to 1, then you let y1 to be 2. And if x11 is not equal to 1, then you let y1 to be equal to 1. So in any case, this first decimal place y1 is not going to be equal to the first decimal place of G1. So therefore, at least y will not be equal to G1. Again, what you have done is you have taken the second place, y2, second decimal place, to be such that if you look at G2, then G2 is going to be point x21, x22, etc. So if you look at the second decimal place after the decimal point for G2, then this second decimal place y2 will not be equal to x22. That is what we are ensuring, that if x22 is equal to 1, then you say that choose your y2 to be equal to 2, and if your x22 is not equal to 1, then choose y2 to be equal to 1. So you're just choosing this number. So in this fashion, your second decimal place will differ from the second decimal place of G2. Therefore, y will not be equal to G2. Similarly, y will not be equal to G3 and so on. So the way you construct it, you see that y will not be equal to Gn for any n. This is clearly a real number sitting between 0 and 1. There is no problem with that. These are all either 1 or 2. So this is a very well-defined real number, and this will not be equal to any of these numbers. So therefore, what can you say? That y is not in the image of G. So what does that mean? That means that there is at least one element in the open interval 0 1 which will not which whose pre-image will be empty. So whatever mapping you take from the set of positive integers to 0 1, it cannot be surjective. So you don't get a surjective mapping from the set of positive integers to 0 1, which implies that the open interval 0 1 cannot be countably infinite, which means that it is uncountable. Okay, so from here we can immediately deduce that if you take any of these sets, closed interval 0 1 or the semi-open intervals 0 1, like this. Remember, here you are leaving out 1 and here you are leaving out 0, and here you are including both 0 and 1 and all the real numbers between 0 and 1. So any of these intervals will also be uncountable. Why? Because in the last lecture we had seen that subset of a countable set is countable. So open interval 0 1 is a subset of any of these. So what have we written? We have said that suppose J is any of these three intervals, then the open interval 0 1 is a subset of it, and open interval 0 1 is uncountable. So its superset has to be uncountable, because if J was countable, then its subset would have to be necessarily countable. But we have seen that open interval 0 1 is uncountable, so that implies that any of these three sets is also uncountable. Okay, so similar reasoning tells you that the set of real numbers is also uncountable. Same reason, because open interval 0 1 is a subset of R and open interval 0 1 is uncountable, and we have already seen in our previous lecture that if you look at any subset of a countable set, then that has to be countable. So obviously R cannot be a countable set. So since R cannot be a countable set, that is the meaning of the terminology uncountable. So therefore R is an uncountable set. Okay, so this is proof is very simple once you have done all your hard work, but the result is very important. Okay, so what was crucial about open interval 0 1 or any of these intervals, closed interval 0 1 or the semi-open intervals 0 1, is that there is nothing significant about it. If you, instead of that, if you take any bounded interval, then the same result is true. So how will you show that? What you do is, and this is something which we will use many times during our course, in this particular course and also the future courses. So therefore I have specifically written down the details of this. What we will do is, we will not again prove it from scratch. All we will show is that these bounded intervals are of four types. You take any a less than b, you will either get the closed interval or the open interval or the two semi-open intervals. So these are equipotent with similar type of intervals with endpoints 0 and 1. That is what I want to show, and that is going to be very useful to us in various contexts. So how do you show that? You just see, give a linear mapping from 0 1 to AB. So 0 1 is a line segment, AB is another line segment. You just take a linear mapping, means if you draw the graph of F, it should be a straight line. And what are you going to do is, you send 0 to A and 1 to B. So that is just this particular expression that look, this is your division of the line segment in two parts. 1 minus t is to t. From there you get this formula. So f of t you define to be 1 minus t times a plus tb. So what is f of 0? F of 0 is going to be a and f of 1 is going to be b. That is clear from here, and this is actually a bijective mapping, so I have specifically written down its inverse. So before that what I did was that I wrote it in this fashion. So this makes it a little bit interesting in the sense that what you are doing is that the length of this interval is b minus a, so you are just giving an increment of t times b minus a to a at time t, if you like to think of it like that. So that is why I have written it like this. So that is one way of observing it. See, these two expressions are the same, and what you are trying to say is that f is bijective, so you just specifically write down the inverse of that. So how do you do that? You again give a linear mapping. So you just take a map from the closed interval AB to 0, 1. You want g of A to go to 0, g of B to go to 1, and you want a linear mapping. So linear mapping means what? G of T should look like something, some slope, so m into T plus C. Now you put T is equal to A, so MA plus C should be equal to 0 and MB plus C should be equal to 1. So from there you can calculate what M should be and what C should be. So I am not going to go into that detail, but that is how I got this formula, that I want this to be linear, meaning the graph of this should be a straight line. So we know that a straight line, its general form is y is equal to mx plus c. So my gt is y, say, right? So I want to say that gt should look like that. So it should, instead of x, I am writing t now. So gt should be look like mt plus c. Then you can just simply calculate what your m and c will be, because you want to force that a should go to 0 and b should go to 1. I want it like that for the time being, because it was not necessary, but here also I did that I sent 0 to a and 1 to b. So here also I want to do the same thing. I want to send a to 0 and b to 1. So your ma plus c will be 0, mb plus c will be 1. So calculate from there, you will get the value of m and c, and you will see that the formula will look like this. So gt is equal to 1 by b minus a times t minus a divided by b minus a. So if you write it in a shorter form, it looks like t minus a divided by b minus a. It is obvious from this that g of a is equal to 0 and g of b is equal to 1. And then it is a simple job to just check whether G composed F and F composed G are identity maps or not. So I have done that in details. That suppose I take T between 0 and 1, then G composed Ft will be what? G of Ft. So Ft by definition was A plus T times B minus AC. This was our formula. So we just put it here, and then we apply the formula for G. So the formula for G was T minus A divided by B minus A. So here T has become this expression. So you are writing A plus T times B minus A, whatever was there in the bracket, minus A divided by B minus A. Now do the calculation. It will not be difficult. A and A will cancel out. So you are left out with T times B minus A divided by B minus A. So you will get T back. So G composed F of T will be equal to T when T is between 0 and 1. Similarly, when T is between A and B, then if you look at F composed G of T, then you write down this is going to be equal to F of GT. So what is GT? It is T minus A divided by B minus A. So apply F on that. So it will be A plus whatever is in the bracket here times B minus A. So here B minus A will cancel out. So you will be left out with A plus T minus A. So that will give you only T. So again F composed GT is equal to T. So what have you got? You have got a bijection. From Where to where? From close interval 0, 1 to AB. So close interval 0, 1 and AB are in 1, 1 correspondence. So they are equipotent sets. Not only that, 0 maps to A and 1 maps to B. So therefore, if you leave out 0, A will be left out from the image. If you leave out 1 from the domain, then B will be left out from the image. That is what I'm trying to say here, that if you just restrict your map F to the open interval 0, 1 or these two semi-open intervals, then they are also going to be bijective mappings. The way you have constructed that 0 goes to A and 1 goes to B, that is helping us in this. Of course, you could have taken the slope to be the other way around. That is, you could have sent 0 to B and 1 to A. But why complicate life? So we will just take this straightforward one. So this F has this particular property. Therefore, all these three mappings where the domain you're restricting is going to give you a 1-1 correspondence with this corresponding ranges, corresponding images of F. So all open interval AB, for example, is equipotent to 0, 1. This semi-open interval is equipotent to this one. This is equipotent to this one. And close interval AB is equipotent to close interval 0, 1. Now, all of these are uncountable sets. So recall by our previous lecture that if you have two equipotent sets, either both of them are countable or both of them are uncountable. So since these are uncountable, any bounded interval is uncountable. So once you have proved this, you notice again by the same type of reasoning which we gave a few minutes back, that the subset of a countable set is countable. So if you take any unbounded interval, unbounded intervals will look like what? They are also of four types: open interval a to infinity, or close interval a to infinity, or open interval minus infinity to a, or close interval minus infinity to a. Right? Either you include a or you don't include a. Why? You express that by a first bracket. So any such unbounded interval is bound to have, so let me not use the term bound again, it might confuse. Any unbounded interval will have a bounded interval as a subset. So therefore, now bounded intervals are uncountable, so naturally unbounded intervals will also have to be uncountable. That is what we are trying to say. Okay, so the next thing is actually a trivial example. If you had taken, but this causes some confusion, so I have included it here, that if I had taken a bounded non-empty finite subset of R, if I take a finite subset of R, which is non-empty of course, then you can just list out your elements of the set from the smallest to the largest. That is one way of listing. So you will always get a minimum element and a maximum element. So we have discussed this, that the minimum element will in fact be the infimum and the maximum element will be supremum. So if you have a non-empty finite subset of R, then the supremum and infimum will always belong to the set, because supremum is going to be the maximum of that set and infimum is going to be the minimum of that set. So the question is that instead of finite set, if I take countably infinite set, then what will happen? Since I'm taking a countable set, a tendency is to think that maybe the infimum and supremum might belong to the set. See, if you don't have a countably infinite set, then the supremum and infimum will not belong, is what we have already seen. That if you take any, take for example this one, take the bounded interval a to b, open interval. Then here your infimum is a and supremum is b, this you have checked. in a previous lecture, and this infimum A does not belong to the open interval AB, and the supremum or B does not belong to the open interval AB. So the infimum and supremum of a uncountable subset of R may not belong to the set is clear from this example. But what happens if I take a countably infinite set? Even in that case, the infimum and supremum may not belong to the set. So I have constructed this example, and if you observe, then you will see that you will be able to construct many such examples. What I am basically doing is I am looking at all 1 by n's. So you have half, 1/3, 1/4, and so on. So this is decreasing to 0. And here I am looking at all 1 minus 1 by n. So these numbers are increasing to 1, right? So it is 1 minus half, 1 minus 1/3, 1 minus 1/4. So it goes on increasing to 1. So you take these two sets and take the union of that. So first of all, note that this is countably infinite, because just define the mapping 1 by n going to n. Then that is an injective mapping from this set to the set of positive integers. Again, here what you do is you send 1 minus 1 by n to n. Then this is also an injective mapping from this set to the set of positive integers. So this is countably infinite, and this is also countably infinite. So if you take the union of that, there are only two such sets, and you are taking the union, so you will again get a countable set. So not only countable, it will be countably infinite. So A is a countably infinite set, and it is very clear from the description of the set that 1 is going to be the supremum of A and 0 is going to be the infimum of A. So 0 and 1 do not belong to the set A. So since this causes some confusion sometimes, I have given this example that if you take a bounded countably infinite subset of R, the supremum and infimum may belong to the complement of the set. Okay, so this is all about countable and uncountable sets for the time being. In the next lecture, we will continue with our discussion. We will do some more results, and we will show that uh, the set of real numbers is equipotent with open interval 0, 1. So let me stop here.